Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover differentials and their relation to derivatives. So in a previous video, we talked about how we can approximate a function near a center x equals a using a tangent line. So the linear approximation, or your tangent line L of x, is equal to that y-intercept, which is f of that a, plus the slope, which is going to be f prime of a, multiplied by x minus a. And that linear approximation could be, this line right here, this L line, would be this tangent line to this particular curve. Now, as long as I'm really close to this value x is equal to a, as long as I'm, centered around here, the values of the linear approximation and the values of the blue curve will be very, very similar. So this really extends to finding differentials and why the formula is the way it is. So what we know is that, f of a plus your change in x can be approximated by, your L of your L of a plus your change in x. So what this means is your change of x being really small. So this is your a plus the change of x might be right here. So this means a plus the change of x. Now it could be a little above or a little below, but we know as long as we're really close to this, the output of the line and the output of the curve are going to be very, very similar. So we know that this linear approximation is going to be equal to, well, it's right here. This is going to be, f of a plus f prime of a. Remember, these are your constants. Your input happens to be this x, and our input is going to be a plus the change in x. So this is going to be a plus your change in x minus your a. So what I can see is that over here, remember, all we did is just input that for, for this x spot here using, our input. And we can see that these a's are going to cancel. So what I'm going to get is I'm going to get f of a plus f prime of a times just your change in x. Now what I'm going to do is I'm going to isolate this piece over here. So I'm going to send this to the other side. So, f of a plus your change in x minus f of a can be approximated by, remember there really is a squiggly, these things are equal to this L, but this approximation can be equal to f prime of a times your change in x. Now over here, this is nothing more than your change in y, so your change in y is going to be equal to f prime of a times your change in x. Now as long as x is getting really, really, really small, the closer we get to this, the closer we get to this point here, the closer the approximation. So what we actually say is, as this gets really small, as it gets to the differential form, as opposed to like some large change, some itty-bitty infinitesimal change, we can say that df is actually going to be, instead of being approximated by this, is going to be equal to, f prime of a dx. And this really forms the formula that we use for differentials. So let me put that up there. So here's our definition. It says let y equal f of x be a differentiable function, then the differential dx is the independent variable, and the differential dy is found by, dy is equal to f prime of x dx. And we can kind of see where this thing came from. This came from what we just did. So really the idea is if you can find a derivative, you can also find the differential. All we do is really just have this dx next to the derivative. So, and I'll kind of show it algebraically as well as if you want to do it that way, but it's really a verification of why this dx gets to the other side instead of like multiplied by dx. But let me explain. So if I want to find this thing differential, dy is just going to be the derivative of this followed by dx. Well, the derivative of this is going to be 20x cubed plus 3 and then a dx. Now, other ways that it tends to get shown is, if I know y, then I know dy dx, which is going to be the derivative of this thing, would be equal to that, 20x cubed plus 3. Therefore, if I want to isolate dy, we just put the dx to the other side. And, it algebraically works out that way due to this formula right here. So that's two different approaches. So really, the way I do this is I find that if I want to find the differential dy, I just find this thing's derivative and then put a dx over here. That's really as easy as that is. So remember that in order to find differentials, you use the exact same rules you do for derivatives. So right here I have a product, therefore I have to do a product rule because I need its derivative. So the derivative of the first times the second plus the first times the derivative of the second. And then you know we're followed by our dx. So that's that thing's differential. So if you enjoy the content, please subscribe.